All right, guys, all right. If you can turn your videos on, turn your videos on. If you can turn your videos on, turn your videos on. Stand up, don't breathe on each other. Stand up, don't breathe on each other. Stretch, if you can, just stretch. This is going to be a long day. This is going to be a long day. So I'm going to need you to focus. I'm going to need you to focus. Okay, let's sit back down. Let's sit back down. Okay, now if I do this, guys, can you still take notes? Can you still take notes like that? Okay, so let's that way I can see the rest of the class. That way I can see the rest of the class. I forgot, guys, I forgot to make a video. I forgot to make a video with my iPad. I should just have Zoom record, but it just doesn't record well enough for you guys to actually be able to see. And so I apologize. If you weren't in class, make sure you get notes. If you weren't in class on Monday, make sure you get notes. We have a WebAssign due when? We have a WebAssign due when? Friday. Guys, I finally figured out how to set a time different than the start of class. So from now on, they're going to be due at 11:59 on the day instead of class time. So that gives you part of Friday to also get your WebAssign in. Okay, so it's due by 11:59. A little bit about where we've been. We've been talking about space curves. Say that.
Space curves.
When I say space curve, you say R of t. When I say space curve, you say R of t. When I say line, you say
A plus TD.
which is a special kind of space curve. When I say plane, you say n dot x minus a equals 0. What's n's role in that? It's a normal vector. So it's normal to the plane. This is our definition of a derivative. Of a space curve. Okay? R prime of c is defined, not surprisingly, in terms of a limit. Okay, it's a scalar limit though. The domain is real value. So it's a limit as t approaches c of the numerator. The numerator is the difference of two vectors. So the numerator is a vector, and we're dividing it by the scalar t minus c. Now we notice this is opposed in that as t approaches c, the numerator goes to which vector? The numerator goes to the 0 vector, but the denominator goes to which scalar? The 0 scalar. So it's a 0 over 0 kind of limit, but much different than 235. This is a vector, this is a scalar. If this limit exists, it goes to this vector, and we just denote this vector f by r prime of c. This is a vector. Say that.
This is a vector.
Say it again. Okay. So this is our definition. In this class of a vector value function. R of t is a vector value function if and only if R of t is equal to an order triple of 3 real value functions. So your vector value functions, if you're an order triple of 3 real value. You're a vector if you're an order triple of 3 real numbers. So this makes complete sense. This will give you a real number for every t. This will give you 3 real numbers for every t. I worked pretty hard justifying the derivative theorem. Our derivative theorem, I call it the derivative theorem, that r prime of t, if I use this definition, is equal to x prime of t, the derivative of that first real value function, y prime of t, and z prime of t. Would you rather use the definition or use the theorem to calculate derivatives? Would you rather use the definition or the theorem? The theorem. So you guys, let's do something. You guys give me a vector value function, or you guys at home. Somebody give me a vector value function. Just give me a vector value function.
X2, X3,
X, 2, x, 3. Make it in terms of t, rather. Make it in terms of
T, 2T, 3T.
2t, t, 3t. So true or false? Is that a vector value function? Okay, let's ramp it up a little bit. Let's ramp it up. Maybe we'll make this t to the, maybe we'll make this t to the third, this t to the second, and this t to the first. Okay, like that. Okay. So now we could go over and use this or that to find r prime of t. To find the vector valued function r prime of t. Would you rather use this or that? Would you rather use this or that? Then use that and do that. Use that and find the derivative function. And I'm hoping everybody's done. I'm hoping that everybody would be done. What is the derivative function right here? What's your name?
Lizzie.
Lizzie. What do you have for the derivative function?
3t squared, 4t, 3.
And 3. Did everybody else get that? Okay, so there's my derivative function using my derivative theorem. Okay, I told you what's not going to be on the next quest. Proofs. Okay, but math is proof. I'm going to give you guys 5 identities, 5 theorems that represent the heart of what we're going to do later. But I'm only going to prove one of them instead of most of them, which is what I would typically do. I can't in good conscience not justify one of them. I just can't. Okay, that's just not who I am. But the rest of them, no, this will not be on your quest. Which is dangerous for any teacher to say, because then you're like, well, I was up late last night. I think I'm not going to zone, Dr. Warren. I think I'm not going to pay attention anymore to you for the next 15 minutes while you work through this proof. But I want you to be thinking like it is going to be on the quest. I want you to be responding like it is going to be on the quest, because will there be other theorems and proofs in this class? And I need you thinking this way. So this is what I've got. I've got this theorem. I'm given what? A vector value function, r of t, and a real value function, alpha of t, and then I'm going to look at the derivative of the product, the scalar times the vector value, the scalar value function times the vector value function. And I want to prove what that product's equal to. What would you guess? I mean, if you had to guess, sometimes it's good to know at least where we're heading. If you had to guess what the derivative of a scalar function times a vector function is, well, let's go back. What is a scalar times a vector? Geometrically, what's a scalar times a vector? A vector.
Yeah.
So if you have a scalar value function times a vector value function, what do you think you're going to get? Another vector value function. Doesn't make sense. Like if I went up here and if I took Roberts and like, give me a scalar value function. Give me a scalar value function. 5, okay. Maybe make it just a little bit more interesting, Emily. 5t squared. What would this scalar valued function times the vector valued function be? Could you figure that out? Could you guys figure that out? You'd be like, Dr. Warren, that's not bad. It would just be 5t squared times this, which would be, I know this is hard. You're in Calc 3. 5t to the, and then I would have
10t to the fourth.
And then I would have
15t to the third.
And would the result be another vector value function? Would the result be another vector value function? Okay, so this is what we have. Now I'm asking, how does the derivative respond? How does the derivative respond to a scalar times a vector? If there was any mercy in mathematics, what would the result be? If there was any mercy in mathematics, let's go back to 235. How many people remember how to take the derivative of that? How many people remember how to take the derivative of that? What's the derivative of f times g? What's the derivative of f times g? Anyone?
Is it f prime g?
F prime of x times g of x, and then, I'm sorry, what's your name again? Raylan, yeah, awesome, Raylan, awesome. How many people remember that? How many people remember that? Well, let's apply it here. This is not the proof. Help me understand. Writing this down is not the proof. So what would you guess the derivative of an alpha t scalar times a vector value function r of t to be? What would you guess it might be? The derivative of the scalar times the vector plus the derivative of the vector, and I'll put the scalar first, times r prime of t. This is what I want to prove. This is what I want to prove. And guys, it's going to take 15 minutes to do this. It's going to take 15 minutes to make this proof. And we're doing it together. We're doing it together. We're going to be like, did anybody in here see the worst movie ever made called Pacific Rim? Or was it just me? Am I the only human being that saw Pacific Rim? Probably am, aren't I? What happens is there's these giant monsters that are coming up, giant, and we have to save them. And I'm in a robot, but I can't drive the robot by myself. There's somebody else who joins me and the other thing. And we mind meld, and that gives us the ability to work the robot. We are going to mind meld together. We're going to mind meld it. Except Cosmo, I'm not mind melding with you right now, Cosmo. I'm mind melding with Stuart. Stuart, I'm mind melding. But you don't have to answer all of them. You don't have to answer all of them. I'm going to do the logic. You guys are going to, when you make a proof, some of you guys are still learning as I grade the quest. Some of you are still learning. When I say prove, you need to provide both logic and justifications. It's not just logic, it's logic and justification. I'll do the logic, you do the justifications. Okay, so this is what I want to prove. Here's my proof. Given r of t is a vector valued function, given r of t is a vector valued function, then there exists, I'm getting lazy because I need to save time, there exists real valued functions x of t, y of t, z of t, such that, that's an s dot t dot, such that r of t is equal to the vector x of t, y of t, z of t. Okay, so I made the first move. I made the first move in my chess game. Okay. We were given that r of t is a vector valued function, then there must exist these three scalar valued functions, x, y, and z, such that r of t is equal to this by what? Now I've done the logic, you give me the justification. What am I using, guys, to guarantee these real valued functions must exist? What are we using?
Definition of a vector value function.
Very good, Gordon. Over here, is that not our definition? Is that not our definition of a vector value function? And so here we would put by definition of a vector value function. Now there's no way, guys, I'm going to be able to get all of what I need just on this board. So I'm going to have to come back and erase. Math is proof. When you're trying to show an equality, when you're trying to prove an equality, you're trying to prove this side is equal to that side, you can always start with one of the sides being given to you. You can either start here and work to there logically, or you can start here and work to there. So I'm going to start with this side, and that's given. There's my justification. I'm doing both. Given alpha of t times r of t prime. I want to find the derivative of that. Well, then this would be equal to, now here comes the logic. the derivative of alpha of t times the vector x of t, y of t, z of t. This derivative would be the same as that derivative. What am I using, guys? What are you using as your justification to say that this would be the same as this?
Definition of vector value function.
Well, we've already used up our definition of a vector value function. We've got that there. What am I using to go from there to there?
Substitution.
I like where you're going, Nick, but Robert hit it right on the head. Say it again, Robert.
Substitution.
By substitution in my vector space. Does that make sense? Does that make sense in substitution? So by substitution in V. Since this is R of t, then I'm substituting it in for R of t there. Okay, now I'm changing games. We're changing seats in Pacific Rim. I'm gonna provide the justification, and you guys are gonna provide the logic. I'll provide the justification, and you guys are gonna provide the logic. So my justification, I'll put the equal to down. My justification is going to be by scalar multiplication. My justification is scalar multiplication. What's the line of logic that would follow? What's your name back here?
Sean.
Sean, love the shirt. I'll even love more if you give me the right vector. What would you have there, Sean? What would you have there?
Alpha tx t.
Alpha tx of t. That's the first component in our vector value function. And then
Alpha ty of t and then alpha tz of t.
alpha ty of t and alpha t z of t. Did anybody else get that? Is there anybody else who was heading that way? Okay, so now, sorry, my equal sign's got to go way over here. I know this isn't right. We'd love to line them up. So you can line them up in your writing, but I can't. I'm going to go here. This is, I should make you guys do this, but I'm going to do this one. I'm going to say my line of logic is by my derivative theorem. So I'm going to use my derivative theorem to go from this line of logic to something that's equal here. This is a tougher shot. I hit a lob over your head. See if you can dig it out. I hit a lob over your head. See if you can go dig it out. Be serena. Go dig out that ball in the back of the court. We're using our derivative theorem. Michael, do you have anything for me? Michael?
I just did the chain rule.
Chain rule, okay. So what do you have as your first component?
I said alpha prime x of t.
Okay, so yeah, we
Plus
can't.
x prime of t, alpha t.
Okay, yeah, you're actually ahead of me. You're 2 steps ahead. Before we do that, you already did a step in your head. We would have, first of all, just using the derivative theorem, we would have a derivative of, very good, Raymond, alpha t times x of t. So let's do this in 2 steps, Michael. You're there, Michael. You're ahead of me. We're there. And then Zach, what would I have here? Zach, what would be the next one?
You would have alpha t and then y of t, and you're taking the derivative of that.
Perfect, Zach, perfect. And then I'll do the last one, alpha t, z of t prime, alpha t, z of t prime. How many people are following? How many people are following the logic here in this class as we're moving ahead? Okay, now, Michael, you weren't using chain rule, but you were using what rule from 235? It wasn't chain rule, but what rule was that?
Product.
Product rule. So you guys use product rule. So this is my product rule from Math 235. So that's our next equality. Guys, if you guys can turn on your cameras, turn on your cameras. I want to see your faces. You're in class. I want to see you in class. I want to see you in class. Josh, good to see you. Gordon, great to see you. Brandon. Holly, good to see you. Haley, good to see you. Brandon. Patrick, Luke, Greer, Alexander.
My desktop doesn't have the.
Okay, no, I understand that. Okay, hold up what you have. Go to grid view, hold up what you have, and you guys hold up what you have in here. You guys talk to each other, so show each other what you have. What do you guys have? What do you have? What do you have? Okay. Now, if you didn't follow the logic, I'm not sure in the grid you guys are going to be able to read this at all. I'm not sure in the grid you're going to be able to read it at all. Because it's looking at, you guys always, when I saw what it looked like in the grid, it looked like I had cataracts in my eyes when I was looking, trying to figure out what was written on the board. I don't know how you guys get notes. We're using product rule. This is the derivative of the first function times the second. The disappointing thing in product rule is there's a plus. The first function times the derivative of the second function. And then I just used that 3 times. That's the kicker in Calc 3. The work is always multiplied by 3. It's always multiplied by 3. Okay, now in any proof, let's go back and see where we want to get to. What's our goal, guys? What are we trying to reach? We started here, and we're trying to reach where? We started here, and we want to reach where? The other side. Now look at where we're at. Do you guys see us moving in the right direction? So now, I'm going to let you do both lines of logic, but you guys are going to, as a class, is going to start this. What do you think our next justification? Look at where we are. Look at where we want to go. What do you think the next line of logic would be? What do you think the justification of that line would be?
The definition of vector addition?
The definition of is it red?
Yeah.
Definition of vector addition. So just put a vector plus so it doesn't look like a cross. Put a vector plus so it doesn't look like a cross. And now try to use what Rhett suggested. Break that vector into 2 vectors. And guys, this is active learning versus, if I just wrote it on the board and you copied it, that's passive learning. You're just doing what I did. But this is active learning, which forces you guys to engage. So when you're teaching, I want you guys using active learning. For sake of time, what do you guys have as the first three components in that first vector? What do you have as the first three components in that first vector? Alpha prime of t, x of t. Y of t, and then alpha prime of t, z of t. Did anybody else get that? Is it Caitlin? Yeah, so anybody else get that? Do you guys see that? David, does this make sense? Okay, and then that would force what? That would force what, guys, to be the remaining vector? That would force what to be the remaining vector? Ouch. Perfect, Raylan. Alpha t, x of t. Alpha t, y of t, and then alpha t, z of t.
Yes. It needs to be.
Oh gosh, yes. Thank you. I need you guys. 1.9 high school grade point average. I was just thinking how bad my knee hurt when I kneeled on the cord here. Okay. Now let's see what I taught you. What would be the next justification if I suddenly, let's not believe this, but I suddenly passed out and you had to complete the proof by yourself? What do you think your next justification would be if Dr. Warren passed out on the floor? Look at where you want to get to and look at where we're at. What do you think the next justification would be?
The definition of scalar multiplication.
Good, Rhett. Scalar multiplication. Write that down. Write down by scalar multiplication and then use it. Then use your scalar multiplication. So Nick, what do you got for me, man? What do you got for me, Nick?
I'm drawing a blank.
You drawing a blank? Look what's alike in each one of these first vectors, Nick. Look at that first vector. What's alike in each one of those?
You just take out the scalar prime.
Yeah, just take out that alpha prime. Take out that alpha prime. So I would have what? I would have what here, Bridget? Do you have anything for me? Alpha prime of t, perfect. Perfect. Times x of t, y of t, z of t. Perfect. Awesome. And then, Emily, what would you have in this second vector for me?
Alpha t times the vector x prime t.
Perfect. Alpha t for you guys at home. I'm just saying it loud. I'm gonna use my voice to fix cataracts. Alpha t times x prime of t, y prime of t, z prime of t. Are you guys following? Are you following this argument? Are you following at home? Are you guys following it? Okay. Do we look pretty close? I mean, if we're looking where we want to get to and where we are. And you're like, Dr. Warren, you're out of space. And I agree, I am out of space. So I've got to erase something. And I guess I'm going to erase this, which I know I'm going to regret later. We're going to crash land this proof. We're crash landing it with one step. We're crash landing it with one step. So we're going to go from this line to the end. We're going to go from this line of logic to the end. And since everybody knows we started here and we wanted to end where? We started here and we wanted to end where? Yeah, we wanted to end over here. So let's just write down the logic. Then this would be equal to alpha prime of t times r of t plus alpha of t times r prime of t. Okay, now comes the hard part, the justifications. I need two justifications. What's clearly one of them? What's clearly one of the justifications? If you're going from here to there, what's clearly one of the justifications?
Definition of a vector value function.
Definition of a vector value function, I like that. Definition of a vector value function. But we already kind of have that on the board. It's not Patrick.
There's Sean.
Sean, we already kind of have that in the proof on the board. We've kind of got that there. What else, what have we done to like replace this guy with that guy?
Substitution.
By substitution. So write that down. That's one of the things I'm definitely using at this line. I'm going back and substituting from what we have above. Now comes the more subtle part of the argument that would only be worth like 1 point or a half a point out of 10. We haven't yet defined r prime of t. If you look at our logic, do you see how r prime of t is not on the board? R prime of t hasn't been brought on the field yet. Hasn't been brought on the court. So we're trying to figure out what do we do to say that like r prime of t, if r of t is this, then r prime of t is x prime of t, y prime of t, z prime of t. What would allow me to say that if r of t is x of t, y of t, z of t, that r prime of t would be x prime of t, y prime of t, z prime of t? The hardest shot of the whole proof. The derivative theorem, by the derivative theorem. Very good, Nick. And I'm also using and by my derivative theorem. And by my derivative theorem, which is what we have down here. And by my derivative theorem. I mean, guys, how many people understand the proof? How many people kind of understand what we're doing here? Sorry, I'm like 8 feet away, guys, so don't get horrified at home. I'm dropping my mask. Okay, I'm dropping my mask. How much have you guys learned? I mean, how much have you learned just being in the classroom? If you think about making this argument, imagine day one, I said, prove this. You'd be like, what is that little squiggly there, right? I mean, that's what we'd be saying. What is that? So you guys we've learned a lot. If some of you, if I said proof, you'd be like, what's that? What's that? I didn't do that in 235. I don't remember doing that. What do you mean justifications? Let's suppose you end up being a lawyer. Do you think lawyers need to think like this? Do you think lawyers need to think like this? Okay, so I went through a divorce, and then my daughters were being homeschooled, which is fine. I'm not against homeschool, okay? But they were just being homed. There wasn't much school going on. So they were being homed. So then I had to get an attorney to help me get my kids back into public school. Was I happy that she could make an argument? Was I happy that she could make an argument? Little did I know that the Homeschool Defense Association, which I didn't even know existed, out of Washington, D.C., sent a team of lawyers down to like go against my lawyer. Was I happy she could make an argument and justify every single step along the way? Was I happy she could do that? Okay, now, this is what, you don't want to hear this, okay? But do you know what percentage of Americans need bypass surgery sometime during their life? Do you know what percentage of Americans need bypass surgery sometime during their life? 25%. At some point during their life, roughly needs some kind of bypass surgery. Do you want a cardiac surgeon who can create an argument? Do you want a cardiac surgeon who can create an argument? Do you want a cardiac surgeon? Do you know what the first thing they do is? Never mind. I'm sorry, I don't know. Upstairs in Burris, I don't know if you know this, there's anatomy labs. There's anatomy labs. Did you guys know that? There's anatomy labs upstairs. There's anatomy labs. And I went up there one time and the door was open. And on the front of the door it says no food allowed. No food allowed. And then I looked in there and there were dead bodies on the table and people cutting into dead bodies. There's dead bodies in Burris. I was like, oh my gosh. I never want to be in here at night. I never want to be in this building at night. And then I'm like, who the hell would eat while they're taking a dead body apart? Here, can you pass me that ham sandwich? Oh, that's the spleen. That's the spleen. And then they had like it's so gross. They had Home Depot buckets. Sorry, Rachel. I don't know if you ever had that. They had home bucket, and they were throwing crap into throwing body parts, liquid crap into the Home Depot 5-gallon bucket. I'm like, when I signed that card, are you willing to be, let your body be used for science? I never dreamed of a Home Depot bucket is where my body was going. Okay, sorry, enough here. My point is that in every single job, it's going to require you to do. It's going to require you. You're going to be better at it if you can actually create a proof. There's no place to learn it except in a math class. Okay, stand up and don't give each other COVID. Stand up at home. I know it's a lot harder. Stretch. Okay, sit back down. Guys, I should have never, as far as class is concerned, proved this to you. I should have never done it. I shouldn't have taken time because I said it wasn't going to be on the quest. Now, I'm going to write down results I'm not going to prove. I'm going to write down results I'm not going to prove. And this is why we're not going to have proofs on the quest. Because it would take 2 class periods that I don't have to make these theorems, and I would never prove all of them. Do we have a vector addition? Do we have a vector addition in this class? Do we have a vector addition in this class? If you add a space curve plus a space curve, guess what you get? If you add a space curve plus a space curve, guess what you get? A space curve. So this is my first, this is going to be a list of theorems. I'll try to write big for you guys at home. This is my list of theorems. My first theorem is this. If you're taking the derivative of the vector sum of 2 vector value functions, if you're taking the derivative of the vector sum of 2 vector value functions, we can prove that's equal to the derivative of the first vector value function plus the derivative of the second vector value function. And if it's minus, it's the same thing. Okay, now just think about that for a second. Would you have any shot of proving that? Do you think you would have any shot of being able to create that argument? And let me just say, by the definition of a vector value function, there would have to be a x1 of t, a y1 of t, a z1 of t, an x2 of t, an y2 of t, a z2. Does that make sense? Could you use vector addition then? Could you use vector addition? Could you use your derivative theorem? Are you beginning to see how that proof might take place? This is the worst. I tried proving this the first time. I proved it. It took me 2 class periods. I'm like, you're a moron. You should have just stopped halfway through. I tried proving it kind of like what I just proved. A vector crossed a vector is a
Vector.
A vector crossed a vector is a vector. So a space curve crossed a space curve is another space curve. Some of you guys don't have this down. Some of you guys don't have this down as far as A cross B. What are the components in A cross B? What are the components in A cross B? What's the first component? A2B3 minus A3B2. It's the second component that you get messed up. It's the second component you get messed up. It's not A1, B3, but it's A3B1, and then minus A1, B3. If you get that minus wrong, could it torpedo a problem? If you get that minus wrong, could it torpedo a problem? And that's where, and then I've got to fish through your logic from that time on. But imagine that I'm taking the cross product. Imagine that I'm taking the cross product of two vector valued functions. What would the first component be? What would the first component be? It would be x2 of t times, x1 of t, x2 of t, holy heck. y1 of t times z2 of t, and then we got a minus, and then you got to take the derivative, and then you got to do all those little product rules, and then you got to regroup them back out to end up with this result, that this is equal to the derivative of the first space curve crossed with the second space curve. Can you guess what's going to happen next? Can you guess what might 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 happen next? Plus, and if there was any mercy, what would follow that plus? If there's any mercy, what would follow that plus? R1 of t cross R2 prime of t. I proved that the first time I taught the class, and you just watched me make a mistake here. It was a nightmare. It was a total train wreck. And you're like, Dr. Horn, I believe that. I've seen you go train wreck before. 3. R1 of t dot R2 of t. R1 of t dot R2 of t. We take the derivative of that. A vector dotted with a vector ain't A. A vector dotted with a vector ain't A. A vector dotted with a vector ain't a vector. This is the only one that's not a space curve. This is the only one that's not a space curve when you take the derivative. Take a guess at what it is. Take a guess. Take a guess at what we can prove that is. Take a guess. Take a shot. I'll give you a hint. Product rule, product rule, product rule.
The derivative of R1t dot R2t plus R1t dot derivative of R2t.
It's Sean, right?
Yeah.
Yeah, Sean, that's exactly right. That's it. Sean. We write it down. I'll say it. Okay, guys, what Sean said, and I'm not sure you could hear him from back there, it's in fact the derivative of R1, the derivative of R1 of t, dotted with R2 of t. And guess what's in the middle again? Guess what's in the middle? Plus R1 of t dotted with R2 of t. When I'm teaching Math 235, and I'm teaching product rule, I'll have students want to do this. And I think it might come from high school. They'll say, okay, well, it's G prime, F times G prime, or they'll say G prime times F. That's what they'll do. G prime times F plus f prime times g. And I'm like, yeah, that's right, that's right. I mean, you got the right answer, you know, it's, yeah, it's the derivative of the first times the second, plus the first times the derivative of the second. But I don't want you to remember it that way. And they're like, why not? If it's right, I want you to remember it as f prime times g plus f times g prime. And they're engineers, and they're like, why are you forcing me to remember it like that when it's okay to remember it like this? It's because I know when they hit Calc 3, I know when they hit Calc 3 with this, they're gonna screw up. Because cross product's not commutative. It's very important that it's R1 cross R2 prime. It's very important. So if you came from high school and you didn't fix that, you want to make sure it's fixed there. It's not near as important in this. R1 prime dot R2 plus R1 dot R2 prime of t. Do you guys sense that? Did you feel that? Did you guys feel that at home? Did you feel that? I felt it. Yes, I felt it. That was the evil spirit of boredom. I felt it coming into the room. I felt it at home. You guys were being possessed by the evil spirit of boredom. We need to cast the evil spirit of boredom out. So get your hands up. Get your hands up. Get your hands up. Okay, now I'm going to do it first, and then you guys are going to follow. We're going to cast it out. We're going to go, whoa! Okay, are you ready? Are you ready? 1, 2, 3, go. Whoa! Okay, one more time. 1, 2, 3, go. Whoa! Now I want you to say, evil spirit of boredom, get out.
Evil spirit of boredom, get out.
Evil spirit of boredom, leave me alone.
Evil spirit of boredom, leave me alone.
Okay, I think it worked for a moment, but I get a sense this may happen again. Okay, I get a sense it's going to come back in. If you don't fill your mind with logic and math, there'll be nothing there, and the boredom will come back in, and they'll go, what are you going to eat for lunch? But you shouldn't be thinking about that. If Dr. Warren's teaching you should be like, no evil spirit of boredom. Okay. I mean, I don't know why chain rule to me always seems like pregnancy, but to me, it's always like, okay, you got G pregnant with F. Okay, this is the fetus, this is the mommy. This is the fetus, this is the mommy. How do you take the derivative of a pregnant function? How do you take the derivative of a pregnant function? It would be you guys should know, you had 235, 236. What's the derivative of G of F of X? G prime evaluated at f of x, then times f prime of x. Now imagine that, this is kind of alien-like, a space curve is pregnant with a real value function. Imagine that a space curve is pregnant with a real value function. So you would have an x of alpha of t, you would also have a y of alpha of t, and then a z of alpha of t. But red's on it. If I wanted to take the derivative of this r of alpha of t, guess what it's equal to? I'm not proving it, but guess what it's equal to? Let this be your guide. Let this be your guide. Very good, Raylan. R prime of alpha of t, and then times alpha, perfect, times alpha prime of t, times alpha prime of t. But guys, this is a real number times a real number. This is a real number times a real number. This is a vector times a scalar. This is a vector times a scalar. This is a vector times a scalar in this. And then we did this one to start class. We did this one to start class. That if you have a scalar valued function times a vector valued function. If you've got a scalar valued function times a vector valued function. How many people now know what that is? How many people now know what that is? And you better know, because I just proved it. We must spent like 20 minutes proving it. I'm just giving you guys, I'm letting your brains rest, I'm letting your brains rest, I'm letting your brains rest. Did I tell you my undergraduate major was not math? Did I tell you that? Did I tell this class that, what was my undergraduate major? Art, okay? But I feel like you don't trust me. I feel like you're like, Dr. Warren, I've seen you draw. I just don't believe your undergraduate major was art. I don't believe your undergraduate major was art. So I have to show you at least a little bit. I have to show you a little bit about how one of the things that I designed, using Calc 3. So what I'm going to do is I'm just going to go back and I'm going to share a code that I wrote using space curves, using arc length, using all the stuff we're going to talk about in chapter 13 to create this object, I'll show you. This is a kind of a commercial because I know you won't learn and boredom will come back. So let me just go back. I'm going to share, it'll be easier for the guys at home. Let me just show you this. It's probably not worth me doing this. I know I'm going to regret this. Let me try to open this up. Okay, so let me try to share this now. Back to this. Okay, so this'll end here. This was a train wreck in my first class. So this is a code. This is just showing you a video of a code that I wrote using space curves and all kinds of other things to create this three-dimensional object. So just look, it's literally 200 pages long. I'm flying through it. It's literally 200 pages long. And then what we're generating is essentially this hyperbola that creates this cross. Let me do it again. I'll show you at the end. But there was no way to create it, so I had to write it in something that we could get a CAD drawing to actually be able to have these pieces. These are the pieces that make up this. These are the pieces that make up this, so a CNC machine could cut them out. Let me stop sharing, and let me show you what it's supposed to look like. Open this up maybe. So this is something that I drew. Can you guys see that? This is something that I drew in Illustrator. This is something that I drew. But yeah, so all of these lines, these are space curves. If this was not done on a CNC machine, it would look horrible. The moment something's flexed out here, it's going to be a visual train wreck. And then how do you get something that's going to sit in 3 dimensions and then project it down onto a plane so that these can be cut out and then welded together? So that's just, this is, so I'm just showing you, let's stop sharing that. Maybe I'll show you this too, just so that. There's something else I drew. I had this bright idea going to the beach, coming back to write a children's book. Let me share this. And so, do you see the book, what it's called? Algae's Bra. So I had this idea of algebra, and I'm like, Algae's Bra. And then I'm like, well, this bra, maybe it could, and so I thought, most people would say, just stop, don't do that. So let me see if I can actually advance this or not. Okay, so there's as the sleepy sun, I wrote it too, so. As the sleepy sun began, prepared to rise, algae gently hummed abroad. Now, I don't care about this. This is something that I drew. This was something that I drew. So you can see this. And then it goes on an adventure. Okay, but maybe back here. Do you see the algebra? Do you see the algebra? Do you see? Okay, never mind. So yeah, it's, yeah. But in the end, okay, well, enough of that. Let me stop sharing. So, my undergraduate major was what? My undergraduate major was what? Art. My undergraduate major was art. My undergraduate major was art, not math. So yeah, you think like most people like, why would you, okay, that was an idea, don't follow through. But no, I had to follow through. I'm like, let me follow through. And nobody wants to publish it. Nobody wanted to publish it. So I know that may be hard to believe. Nobody wants to publish it. Okay, well, enough. Okay. Let's draw an XYZ. Now that we got our commercial, let's draw an XYZ. Give yourself an XYZ. And you might make it pretty big. Don't save paper. Rhett, you're almost out. Okay, now write down R of t. Write down R of t. And let's suppose our domain's A to B. So let's suppose our domain's A to B. So what I've got here is I've got some geometry going. I've got some geometry going. I've got an origin. And I've got an R of t. And there's my domain. Geometrically, what's going to happen? Geometrically, what's going to happen as t runs from A to B? Geometrically, what's going to happen, guys, as t runs from A to B? When I say R of t, you say
Space curve.
space curve. So draw a space curve. Draw a space curve that has a starting point and ending point. Draw a space curve that has a starting point and an ending point. And I'll do the same, Now I don't know exactly where R of A and R of B are, but I'm gonna pretend like the position vector points here when it's B, and it starts here when it's A, so I'm gonna pretend like it's moving that direction. That here I've got my R of A, and here's my R of B, and now let's just pick. So here's my domain. I don't have this axis. Here's my domain, A and B. And now let's pick another point, C. Let's pick C in there. And you guys draw R of C. Let's pick C. And you guys try to visualize R of C on your drawing. You guys try to visualize R of C on your drawing. Okay, now hold up what you have. Hold up what you have. Guys, go to grid view. Hold up what you have. And you guys hold up what you have around the room. See if you guys got anything else. Robert, you share with Lindsay. Just show her back there with you. Lindsay's not even looking, sorry. Lindsay, look at Robert's drawing there. Say nice art. You guys just say nice art to everyone. Say nice art.
Nice art.
Nice art. You could write a children's book. You could write illustrated children's book. Okay. R of C would be a position vector. it's going to point to some point on the curve. It's going to point to some point on the curve. Maybe I'll get mine back here, like there. So this would be my R of C. Oh, crap. I'm not sure you guys are going to be able to. That's like R of C. It points to this point on the curve. When I teach calculus, kids want to memorize a bunch of stuff, and they don't like the definitions. Like if I say, what's the definition of the integral from a to b of f of x? They don't want to memorize that. They want to memorize the fundamental theorem of calculus. It's f of b minus f of a, Dr. Warren, where f prime of x is equal to f of x. Someone don't even say that. They go, I don't know. I'm like, well, what do you mean? You know, what is the integral from a to b of f of x dx? You know, what is that? Nobody wants to remember it's the limit as n approaches infinity of the sum of f of k, f of x sub k times delta x, where delta x is b minus a over n, and these x sub k's are a plus k times delta x. Nobody wants to remember that. But guys, you'll never ever really be able to use it in physics or in applications unless you can understand it there. In the same way, nobody wants to remember the limit definition of derivative, but they're never going to understand the applications unless they do. R prime of C, I kind of put it in your head over here, is equal to what? R prime of C by definition is equal to what? R prime of C, it's in the definition where the physics lies. R prime of C is equal to what?
X prime of C, Y prime of C, and Z prime of C.
I like that, Rhett, but that's the theorem. We use that theorem. I like that. What is the definition? The limit. Calculus is about limits, derivatives, and integrals. Oh my. So this is the limit as t gets close to c in the domain. What's on the bottom? What's on the bottom? T minus c. What's on the top?
R of t minus R of c.
R of t minus R of c. So let's pick a point close. Let's pick a point close to c in the domain. Let's pick a point t close to c in the domain. And let's plug that in. Let's plug that into my space curve. Now I know it's been a long class. I know it's been a long class. But that would give me another what? That would give me another what? If I take a t that's close to c in my domain and plug it into my function, that's going to give me another what? And very good, Robert. Another position vector. Now, because it's close to C, or was that Nick? Nick? Yeah. Robert, were you channeling it? Sorry, you guys weren't in the room. No, so Nick, another. Come on up, Nick. Come on up. Speak to the camera. Let these people see you.
Position vector.
Okay, so what you get another position vector. And because T is close to C, what did I say?
T is close to C.
Dr. Ward, if you repeat yourself another time, I'm going to just come up here and hit you. I'm going to beat you with your own vectors. Because T is close to C, that position vector we would expect would be close to this position vector. So let's draw that as R of T. Okay, now let's look at the numerator in the definition. The numerator in the definition is a vector. Can you put that vector in the drawing? Can you put that vector in our drawing? Okay, show me what you have at home. Show me what you have. Hold up what you have. Hold up what you have. Good, good, Rachel, good. Let me see there. Stuart, yes, yes. Excellent, guys. Show me what you have here. Show me what you have here. Let me see in the classroom. Excellent, excellent, excellent. Okay, you guys again, think how much you've learned. Think how much you've learned. If I would have asked something like this, you'd been like, what? Day one, what? You know, that's what he would, but now you know it's a vector, and you know it connects the two endpoints. You know it's a vector, and you always forget which direction does it go. But remember, it's always with the pi, it always points to the one that's in front of the minus, it always points to the one. So this vector here is r of t minus r of c. That's that vector. Now as t goes to c, then this position vector is going to go to, this position vector is going to go to, as t goes to c, this position vector r of t is going to go to r of c. And so this subtraction vector is going to get smaller and smaller. In fact, it's going to go to 0. You're like, well, Dr. Warren, that's not really going to help us if this vector goes to 0. But notice here, guys. As this vector comes in closer and closer, if I blew up this region here and maybe drew it over here, so this is kind of the same region that I have there. I've got my big point here. Here's my big position vector, r of c there. If I look at this getting closer and closer, maybe this is now r of t. This is my subtraction vector. Do you see how this subtraction vector looks like it's tangent to the curve at that point? Can you visualize to see how this tangent vector looks like it's, I mean call it the tangent vector. This subtraction vector, r of t minus r of c, looks like it's tangent to the curve. And that's what happens. As the limit as t approaches 0, this vector gets smaller and smaller, but it looks like it's on the tangent line to the curve. But in 3-dimensional space. I mean, guys, this is a rope running through the classroom. But you're like, Dr. Warren, it's going to go to 0. Not so fast. What happens in the denominator here? What happens in the denominator here?
It goes to 0.
This goes to 0. This goes to the 0 vector. And guys, it doesn't go to 0, but it goes to a vector. And we can see it. We're going to end class with this. I'll do this. Normally I'd have you guys give it to me. But I'm just going to say t squared e of t sine of t. How many are glad I'm not making you plot that? How many people glad I'm not making you plot that? Cosmo, you don't even know. Okay, Cosmo is glad. Okay. And suppose t is going from 0 to 2 pi. You're like, plot that. No, we're not doing that. How many people would be willing to plot it if I gave you the graphing routine? How many people would be willing to open up the graphing routine and plot it? Okay, so now imagine that I pick a point in the domain. Like pi. Suppose c is equal to pi. How many people are pretty confident they could find that position vector r of pi? How many people are pretty confident they could find that position vector r of pi? You're like, I think I could do it, Dr. Warren. It would be pi squared, the numerical value of e to the pi, and then the only one that we can actually get, sine of pi, and you better know, make your high school teachers proud. Sine of pi would be 0. How many people think they can find r prime of pi? How many people, first of all, how many people think they can find r prime of t? How many people think they could find r prime of t using the derivative theorem? It would be, very good, Raylan, 2t, e to the t. Now comes the hard one. Cosine t, and then we're gonna evaluate this at c, which is pi. So that would be the vector. 2 pi
E to the pi.
e to the pi. Now this is where you guys have to use your unit circle. Cosine of pi,
-1.
-1. -1. Emily, do you see this is not 0? Do you see this is not the 0 vector? Rhett, do you see this is not the 0 vector? So geometrically, the derivative doesn't go to the 0 vector, it goes to a vector of length. It goes to a vector of length. But it lies, that vector lies on the, that vector lies on the
Space curve.
the space curve, but it lies how to the space curve at that point?
Tangent.
Tangent. And like Dr. Warren, how does that, what would that give us physically? So ask me and I'll let class go. So imagine that somebody's writing your space curve in 3-dimensional space. Imagine you have forces. You have forces pushing a cart along your space curve. It's magnetic, some kind of magnetic force through space. There's no other force on us. And then suddenly at this point, we remove all forces on the cart. So imagine we're flying through here along this, going like this, changing R of t. And then we let go of all forces. Physically, then what's going to happen to that cart? It's going to follow that line. It's going to follow that line. Do you think NASA uses stuff like this? Do you think NASA uses stuff like this? Are lines important? Let's end with this. When I say line, you're like, I hate you. When I say line, we need A plus TD. Do we have a position vector for the line? And do we have a direction vector for the line? Could you get the equation of a line? Oh, that's where we're going to pick up. That's where we're going to pick up on Friday. Where do we go on Friday? Downstairs. What do you have to do on Friday? Web assign. Stuart, how are you feeling, man?
I'm good.
Are you sure?
Yeah.
Okay.
Yeah, I'll find out today if I have it or not.
Okay, well, that makes me, just knowing you're good. Caitlin, how's Dad?
It's okay. Yesterday was not good, but he's not hospitalized, so like that's.
Caitlin, that doesn't mean.
Yeah,
So,
it's, I don't know, I just like try to chat with him every day, and like, I
right.
don't know, he's kind of like, oh, I'm fine, you know, and then I hear the real stuff from my mom, and so
Does he still have a fever?
yeah, and so, he had a really bad cold, like, this past weekend, and so
Okay.
that's gotten better, but like, he's really tired. That's what
Sure.
it is now,
Sure.
and like, whoop.
Shout out to Warren.
Yeah.
Aw, thanks, Nick. See you, Robert.
So that's really it, you know.
Okay.
It's, yeah.
Well, it's all been a week.
Yeah, and so hopefully, you know, like, we're like almost done with this, hopefully.
Okay.
So it like gets better, but
We'll know in another week more where.
yeah, won't worry.
So we just get that fever to break. That
Yeah.
would be the.
Yeah, seriously, because usually I've heard that like the fever doesn't last too long, but for my dad, it's lasted like a while.
And that just wears you out, a fever.
Yeah.
So maybe, I mean, I don't know, maybe he can get some of that, the transfusion. Something that will.
Yeah, like the plasma.
Yeah, I know nothing. Yeah, but yeah, like the plasma that has the antibodies already in it.
Yeah.
Okay,
Exactly.
okay.
Well,
Well, we're just, okay. Well,
Yeah,
I'm just gonna keep praying for him until
Thank you.
till I hear that he's better.
Yeah, I really appreciate it. Yeah, I'll let you know if like,
Okay.
anything happens, but yeah, I'm still like crossing my fingers.
Okay.
Thank you.
Thank
Have a good
you.
day.